the expression for effective resistance of two resistors in series combination and parallel combination. Okay, so till 24th question we have just gone through in the last class. So now we will start with 25th question. So that is, you can see there we have considered two resistors R1 and R2 which are connected in series, okay, across a battery V. So as you know that in the series connection the current remains the same, whereas the potential difference differ across each resistor. Okay, so the potential difference across resistor R1 is V1 and across R2 is V2. Okay, so in the second figure you can see there where the two resistors are replaced by an equivalent resistor. Okay, so now it is said that let I be the steady current in the circuit, V1 V2 be the potential drops across the resistors R1 and R2 respectively. Okay, so the total potential difference can be written as V is equal to V1 plus V2. Okay, so from Ohm's law you can see there. So from Ohm's law you can see there V1 is equal to I1 R1. So V is equal to IR, right, from Ohm's law. So applying that itself you can write the potential difference across the first resistor as V1 is equal to IR1, and the potential difference across the second resistor is V2 is equal to IR2. So the total potential difference is V1 is equal to V is equal to V1 plus V2. So hence that can be written as V is equal to I into R1 plus R2, which is considered as equation 1. Okay, so V is equal to I into R1 plus R2, that is equation 1. For equivalent resistance, so you can know that if two resistors are replaced by a single equivalent resistance, so that can be written as V is equal to I R subscript S. Okay, so when you compare both equation 1 and 2, so the LHS are same, so hence you can compare the both. Okay, so hence you can write I R subscript S is equal to I into R1 plus R2. Okay, so hence R and I get cancelled on both, LHS and RHS get cancelled out. The left out thing is R subscript S is equal to R1 plus R2. Okay, so this is regarding the effective resistance of two resistors connected in series. Okay, similarly it is regarding the derive the expression for equivalent EMF and equivalent internal resistance of series combination of two cells. Okay, so now it is regarding the combination of cells, okay, which is connected in series. So now we need to derive an expression for this. You can see in the figure we have taken the two cells where the EMF of cell 1 is E1, whereas the EMF of cell 2 is E2. R1 is the internal resistance of first cell and R2 is the internal resistance of second cell, where V1 is the potential difference across the first cell and V2 is the potential difference across the second cell. Okay, so the total potential difference is nothing but V is equal to V1 plus V2, okay, across both the cells. If the two cells are replaced by a single equivalent cell, so you can see in the figure which is towards the right, that is E equivalent is the effective resistance of that single resistance and R equivalent. Okay, so now as you know that the terminal potential difference can be written as the terminal potential difference equation is V is equal to E minus IR. Okay, applying the same thing itself across first cell and the second cell, you can write V1 is equal to E1 minus IR1. Next, potential difference, terminal potential difference across the second cell is V2 is equal to E2 minus IR2. Okay, so now potential difference across the combination between points A and C. Okay, so the terminal potential difference can be written as V is equal to V1 plus V2. That is nothing but equal to, that can be written as E1 minus IR1 plus E2 minus IR2. Okay, when you combine both V1 plus V2, so it can be expressed as E1 minus IR1 plus E2 minus IR2. So hence the same step can be written as V is equal to E1 plus E2 minus I into R1 plus R2. Okay, which is considered as equation 1. So as you know that if this combination of cell is replaced by an equivalent cell of EMF EQ and internal resistance are equivalent, then the terminal potential difference of that cell is expressed as V is equal to E equivalent minus IR equivalent. Okay, where from equation 1 and 2, if you compare, okay, since the LHS is same, just you can compare. In the place of E equivalent you can write E1 plus E1 plus E2, whereas in the place of R equivalent you can write R1 plus R2. Okay, so this is regarding the expression for equivalent EMF and equivalent internal resistance of series of combination of two cells. Okay, just go through once. In case if you have any doubts, you can ask. Any doubts, students? Yes, any doubts? Okay, fine. We will move to the next, that is state Kirchhoff laws of an electrical network. Okay, so the two laws are important, that is Kirchhoff first law and Kirchhoff second law. Okay, current law and voltage law. The first one is regarding the current law. It is said that the sum of currents entering the junction is equal to the sum of currents leaving the junction of an electrical network. So as you know that it is said that at the junction the current remains zero. Okay, that means that incoming current will be equal to outgoing current. So the current across any junction will be nothing but equal to zero. That is the meaning of that Kirchhoff's first law. Coming to the second law, that is Kirchhoff's second law, it is said that in a closed loop, the algebraic sum of the changes in potential consisting cells and resistance is zero. That is summation of, it is said that the summation of the changes in potential, that is delta V, changes in potential consisting cells and resistances is zero. Okay, that is potential consisting, the change in potential consisting cells and resistance is said to be zero. Okay, that is the meaning of that second law. Okay, so now the last question is nothing but it is written as write the applications of potentiometer. So as I have said in the previous cases itself, okay, I mean in while explaining that chapter itself I said that the uses of potentiometer they are going to ask in your theory also, even in your viva. Okay, practical examination, the viva will be a question will be asked. Okay, that is in case we get the experiment of potentiometer. Okay, so it is said that write the application of potentiometer. So let us see the first application, that is potentiometer is used to compare EMF of two cells. Okay, so potentiometer is used to compare the EMF of two cells. So next, it is used to determine the internal resistance of a cell. Okay, to determine the internal resistance of a cell. So once the college is open, so once you perform the experiment, you will come to know how we are going to compare the EMF of two cell and how we are going to determine the internal resistance of a cell by making use of this potentiometer. Okay, so this is regarding the 2 marks and 3 mark question based upon the current electricity chapter. Okay, so mathematically the second I mean the Kirchhoff second law can be written as summation of V is equal to 0. Okay, or summation of delta V is equal to 0. Okay, so now we will start with the 5 mark questions of this current electricity chapter. Okay, fine. So we will start with the ninth question. Okay, the 5 mark questions based upon the current electricity chapter. The first question is derive the expression for current in a conductor in terms of drift velocity and hence arrive at the expression for electrical conductivity of material of a conductor. Assume the expression for drift velocity. Okay, you need to find expression for current in a conductor in terms of drift velocity. Okay, so now see in the figure you can see there we have conductor where we have applied a electric field. So electric field is directed towards the right side. So as you know that when the electric field is applied, the free electrons which is present inside the conductor drift towards the direction opposite to that of electric field. Okay, and the distance between the two ends of the conductor is written as delta x. Okay, and A represents the area of cross section of the conductor. With this thing, we will start the derivation. Okay, so it is said that consider a conductor carrying steady current. Okay, consider that the current is steady. Next, delta x be the length of the element of the conductor. So one and the same length or the distance between the two ends of the conductor. Next, A is the uniform cross-sectional area of the conductor. Okay, A is the uniform cross-section and N is nothing but number density of free electrons in the conductor. Okay, N is the number density. Okay, so now what we are going to do is small n is nothing but number density. Okay, so now in order to find the total number of free electrons in the element, okay, so as we know that you cannot calculate the what is the number of free electrons present inside a conductor. So now what we are going to do is in order to calculate the total number of free electrons in the element, we are going to make use of that n is equal to charge density into volume. Okay, charge density is nothing but it is n, volume is nothing but it is expressed as A into delta x, where A is the area and delta x is the length. Multiplied gives the volume. Okay. So where the small n can also be considered as number of electrons per unit volume. Okay. So in order to calculate the total number of free electrons present inside the whole conductor, what we are going to do is we are going to multiply that number of free electrons per unit volume multiplied with the volume of the conductor. So that is what they have given here. Okay, so the next is magnitude of charge due to this electrons. Okay, charge is nothing but delta q, that is q is equal to na delta x into e. Okay, so what we are going to do is in order to calculate the magnitude of the charge which is present, that is the magnitude of all the charges. Okay, what we are going to do is we will take this equation multiplied with e. Okay, so that gives the charge of the whole electron which is present inside the conductor. Next, E is the charge of electron. So let us say that if delta T is the time taken by this charge to pass through the element of conductor, then current through the conductor is. Suppose assume that if the electrons take a time take a time of delta T to cross, I mean to pass from one end of the conductor to the another end of the conductor. Okay, if that is the case, what we are going to do is, as you know that how we are going to define the electric current. Electric current is nothing but charge per unit time, right? So hence you can write that one as I is equal to del q divided by delta t, delta q divided by delta t. So as you know that the value of delta q is nothing but what it is, na delta x into e. So hence I is equal to na delta x into e divided by delta t. So that is nothing but equal to nae into delta x divided by delta t. What is this delta x divided by delta t? It is nothing but displacement, right? From one end of the conductor to the another end of the conductor. So hence delta x divided by delta t is replaced by v subscript d, which is known as drift velocity. Okay, so hence I value comes out to be as I is equal to nae vd, which is equation 2. So the next is, as you know that the magnitude of drift velocity which we have come across in the last class. Okay, the magnitude of drift velocity is nothing but v subscript d is equal to e into e divided by m into tau. Okay, v subscript d is equal to e into e divided by m into tau. So now let us substitute this value of vd in equation 2. Okay, so where e is the electric field in conductor, m is the mass of electron, and tau is the relaxation time. So if that is the case, I is equal to NAE into E into E divided by M into tau. So that can be written as I by A is equal to NE square tau divided by M into E. Okay. So as you know that current density is nothing but what? It is nothing but equal to I by A. So I by A is nothing but current density. So hence we will replace that I by A, which is on the LHS, is replaced by J. So J is equal to NE square tau divided by M into E, which is considered as equation 3. Okay. And in equation 4, you know that J is equal to sigma into E. So that is which is the relation between which we have already derived, the relation between the current density, conductivity and electric field. Okay. So the relation between these three is expressed as J is equal to sigma into E. So now what we are going to do is we will compare this equation 3 and equation 4 since the LHS are same. So if that is the case, what happens? You can write sigma is equal to NE square tau divided by M. Okay. So this is the expression for conductivity. In case if you want to express the resistivity, electrical resistivity, so it is obviously the inverse of conductivity, right? So rho is equal to 1 by sigma, right? So hence the value comes out to be as M divided by NE square tau. Okay. So this is an important question. Okay. So even in your examination, this is the expected question, 5 mark question. Expression for current in a conductor and hence arrive at the expression for electrical conductivity of material of a conductor. Okay. So go through this derivation. So in case if you have any doubts, you can ask. Yes, Monisha, why did you join late? Yes, Monisha, why did you join late? You're joining at 12:30. What is the use then? Yes, Monisha, can you hear? Reply. Why did you join late? Monisha. Okay, fine. Any doubts regarding this derivation? So this is a sure question. It's a sure 5 mark question. Okay, fine. We will move to the next question. So that is nothing but what is equivalent resistance and obtain the expression for effective resistance of two resistors connected in parallel. Okay. Sometimes there is a parallel combination. Okay. They'll ask for 3 marks or 5 marks. Okay. So for this parallel combination, first of all, they have said that what is equivalent resistance. Let us go through that. What is equivalent resistance definition? A single resistance which produces same effect, that means allows the same current as the combination of resistance under the similar condition, that is same potential difference, is called equivalent resistance. Okay. So you can see the two resistance which are connected one below the other, okay, in the parallel combination. So if the two resistors are replaced by a single resistor which does the same effect which has been done by both the resistor, that itself is called as the equivalent resistor. Okay, which you can see in the figure, second figure here. Okay, R subscript P. So in this parallel combination, as you know that the current entering through each resistor differs, whereas the potential difference across the two resistors remains the same. Okay, so now it is said that consider two resistors of resistance R1 and R2 connected in parallel across a potential difference of V volts. In parallel combination, the potential difference V across each resistor is same. Let the steady current I in the circuit divide into I1 and I2 through the resistors R1 and R2 respectively. So as you know that the current differs through each resistor. So hence the total current comes out to be as I is equal to I1 plus I2. So according to Ohm's law, I is equal to V by R, right? So applying the same to the first and second resistor. So I1 is equal to V by R1 and I2 is equal to V by R2. So therefore I is equal to V by R1 plus V by R2. Since V is common, we will take out that as common, except that I is equal to V into 1 divided by R1 plus 1 divided by R2, which is considered as equation 1, taking V as common. Okay. So the next is, if the two resistors are replaced by a single equivalent resistor, okay, so the current through that resistor can be, the current through that equivalent resistor can be expressed as I is equal to V divided by R subscript P, which is equation 2. So compare equation 1 and 2. So hence you can write that as V divided by R subscript P is equal to V into 1 by R1 plus 1 by R2. Okay. So cancelling V on both the sides, we are going to get 1 by R subscript P is equal to 1 by R1 plus 1 by R2. Okay. So this is regarding the equation. This is regarding the expression for effective resistance of two resistors connected in parallel. Just go through. In case any doubts, if you have, you can ask. Those are joined late due to late payment of fees, and for the students who have failed in the test. Okay, please go through this revision. It helps a lot. So again, the same chapters will not be done. Okay, we are not going to repeat. So this is the revision what we are doing. So please go through. In case if you have any doubts, you can ask. Okay, fine. The next question, that is 11th one, we will discuss in the next class. Okay, with this I'm concluding today's class. Okay, students.